Hello everyone. In this video, we will be learning some applications of Taylor series. In particular, we will discuss approximating a given function with one of its Taylor polynomials, and then we'll try to get a handle on the error we get in this approximation. Before that, recall that we already have a way to approximate functions, namely the linear approximation. The linear approximation of a differentiable function f near a point A is given by f of x is approximately equal to f of a plus f prime of a times x minus a. In essence, the linear approximation approximates the function f by its tangent line at a. Near the point A, this approximation may be sufficient, but it quickly becomes less and less accurate, unless of course f was a linear function. So how can we get a better approximation? The tool that we're going to use is the nth Taylor polynomial for f. So suppose that f has infinitely many derivatives at a, and that f of x is the sum of its Taylor series near a. If you're feeling uncertain about these topics, you can always go back to lecture F for a quick review. Once we have found the Taylor series for f, we can approximate f of x near a using the first few terms of its Taylor series. That is, f of x is approximately equal to the nth Taylor polynomial, which we're going to denote by t sub n of x, which is equal to f of a plus f prime of a over 1 times x minus a plus f double prime of a over 2 factorial times x minus a squared, and you keep adding terms all the way until you get up to the nth derivative of f at a over n factorial times x minus a to the n. And this is going to be the way that we approximate functions. Also, notice that t sub 1 of x is exactly the linear approximation we saw before. Let's see some examples of Taylor polynomials. First, let's estimate the values of e to the x on the interval -4 to 4 using the fourth degree Taylor polynomial centered at 0. In order to calculate the fourth degree Taylor polynomial, we will need the first 4 derivatives of e to the x, which happen to all be e to the x. And then, plugging this into the general formula for the fourth degree Taylor polynomial, we get that t sub 4 of x is equal to 1 plus x plus 1/2 times x squared plus 1/6 times x cubed plus 1/24 times x to the 4th. To see that this works, let's take a look at the graph of e to the x and t sub 4 of x. Notice that really close to 0, these graphs are very close, but then begin to separate as you get further from 0. Next, let's go ahead and do the same thing except with the 10th degree Taylor polynomial. Well, we've already done about half the work. The 10th degree Taylor polynomial will start off exactly the same as the 4th degree Taylor polynomial, and then it'll have some higher order terms. Now, let's take a look at the graph of e to the x and t sub 10 of x. Notice that t sub 10 of x stays closer to e to the x as you get further from 0, and this is exactly the reason we would take higher order Taylor polynomials, to get a better approximation in our given interval. Let's see some more examples using Taylor polynomials. First, let's find the Taylor polynomial of degree 3 for the function f of x is equal to sine of x at the point a equals pi over 2. In order to compute up to the third order term, we will need to compute the first 3 derivatives of sine of x at pi over 2. So let's go ahead and do that. If f of x is equal to sine of x, then after taking 3 derivatives, we get that f prime of x is equal to cosine of x, f double prime of x is equal to negative sine of x, and f triple prime of x is equal to negative cosine of x. Then, plugging in pi over 2, we get that f of pi over 2 is 1, f prime of pi over 2 is 0, f double prime of pi over 2 is negative 1, and f triple prime of pi over 2 is 0. Plugging this all into the formula for the third degree Taylor polynomial, we find that t sub 3 of x is equal to 1 plus 0 over 1 times x minus pi over 2 plus negative 1 over 2 factorial times x minus pi over 2 squared plus 0 over 3 factorial times x minus pi over 2 cubed. And if we forget the terms that are 0, we get that this is equal to 1 minus 1/2 x minus pi over 2 squared. and so this is the third degree Taylor polynomial for sine of x at a equals pi over 2. Now, for the next example, let's use this Taylor polynomial of degree 3 to estimate sine of 49 pi over 100. Notice that 49 pi over 100 is very close to pi over 2. So, since the Taylor polynomial we just computed is centered at pi over 2, it should give a pretty good estimation for sine of 49 pi over 100. Better than, say, the estimation we will get using the third degree Taylor polynomial centered at 0. So, how do we use the Taylor series to estimate sine of 49 pi over 100? Well, the problem tells us to use the approximation sine of 49 pi over 100 is about equal to T3 of 49 pi over 100, which, if we plug 49 pi over 100 into the polynomial we found in part A, we find that this is about equal to 0.9995. So that is how we will use the Taylor polynomials to approximate functions. Let's try a slightly different example. First, let's write out a general formula for the fourth degree Taylor polynomial of a function f of x at a. This problem isn't meant to be tricky. We can just write down the first 5 terms of the Taylor series to get t sub 4 of x is equal to f of a plus f prime of a over 1 times x minus a, and you keep going until you get to the fourth derivative of f at a divided by 4 factorial times x minus a to the fourth. So that wasn't so hard. But now for part B, suppose that the fourth degree Taylor polynomial of some function f of x at the point a equals 3 is given by 2 plus 2 square root of 3 times x minus 3 plus 10 times x minus 3 squared plus pi times x minus 3 cubed plus 3 times x minus 3 to the fourth. And now the question is, what is the second derivative of f at 3? Well, let's compare the Taylor polynomial we were given with the general formula we wrote down in part A. Where does the second derivative of f show up in the general formula? It shows up here, right before the x minus a squared. Therefore, if we want to find the f prime of 3 in our current example, we should be looking at the coefficient of the x minus 3 squared, which is 10. The final answer is not 10, however, because the coefficient in the general formula is f double prime of a over 2. Therefore, we have to set these coefficients equal to each other, and we get that f double prime of 3 over 2 is equal to 10. And then we can solve to find that f double prime of 3 is equal to 20. And this is our final answer. Now that we have seen how to compute Taylor polynomials and use them to estimate, let's talk about how accurate these estimations actually are. First, recall that if f of x equals the sum of its Taylor series near a, then f of x is equal to the limit as n goes to infinity of t sub n of x. All we're saying here is that the Taylor series is, by definition, equal to the limit of its partial sums, which are exactly the Taylor polynomials. But this implies that as n gets larger, t sub n of x becomes a better approximation for f of x near a. And now the problem is, the further that x gets from a, the weaker this approximation t sub n of x becomes when we fix n. To compensate for this, we must take large enough values of n to get an approximation that is close enough for the values of x that we care about. But how large is large enough? The process that we will use to bound the error will be similar to the one we used for alternating series. First, let r sub n of x be the error in approximating f of x by t sub n of x. Then there are 2 ways that we could estimate this error. First, if the Taylor series happens to be alternating, we can go ahead and use the alternating series estimation theorem from the previous lecture. If it's not alternating, however, then we can use something called Taylor's inequality, which says that if the absolute value of the n plus first derivative of f is bounded by some number m for an interval of radius d about the point a, then the error r sub n of x satisfies the equation absolute value of r sub n of x is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1 for all a in this interval. So that was a lot to process. let's see how to actually apply Taylor's theorem by looking at some examples. All of these examples will involve the function e to the x. So first, let's recall that the fourth degree Taylor polynomial of e to the x centered at 0 is given by 1 plus x plus a half x squared plus 1/6 x cubed plus 1/24 x to the fourth. And now let's figure out how to apply Taylor's inequality to this function. The first part of Taylor's theorem involves finding a bound for the n plus first derivative of f. In our example, we're approximating with the fourth degree Taylor polynomial, so we want to find an upper bound for the fifth derivative of f. So our first problem will be, what is the fifth derivative of f? Is this derivative increasing or decreasing on the interval -4 to 4? And then find an upper bound for the fifth derivative of f on this interval. The first question is pretty straightforward. Since our function is e to the x, any derivative of that function is e to the x. Moreover, we know from the graph of this function that e to the x is always increasing. And so, where does an increasing continuous function attain its maximum? It'll have to be on the right endpoint of the interval. Therefore, the fifth derivative of e to the x, which is e to the x, is bounded above by e to the fourth on the interval -4 to 4. Now, the last part of Taylor's theorem involves finding an upper bound for the remainder r sub n of x. So let's try to apply this part to our example. That is, let's use Taylor's inequality and the upper bound from part A to find the accuracy in approximating f of x by t sub 4 of x on the interval -4 to 4. In order to use Taylor's inequality, we need a good value for m. However, we found in part A that the fifth derivative of f is bounded above by e to the fourth on the interval -4 to 4. So we can use Taylor's inequality with m equals e to the fourth to get that the error r sub 4 of x is bounded above by e to the fourth over 5 factorial times the absolute value of x to the fifth. But on the interval -4 to 4, the absolute value of x is bounded above by 4. Therefore, this quantity is less than or equal to e to the fourth over 5 factorial times 4 to the fifth. And if you plug this into a calculator, you'll find that this is about equal to 465.9. So that's pretty huge. So what if we wanted to do any better? Well, we'd either have to take a higher order Taylor polynomial or consider taking a shorter interval. Let's try shrinking the interval to improve the approximation error. In particular, let's find an interval around 0 for which this approximation has error less than 0.001. Let's rephrase this using our variables. We want an interval, absolute value of x less than or equal to r, on which the error r sub 4 of x is bounded by 0.001. Note that r has to be less than 4, since the error on the interval -4 to 4 was over 400. So, then what is our goal for finding this r? Well, since r is less than 4, we still have that the fifth derivative of f, which is e to the x, is bounded above by e to the fourth on the interval -r to r. So, we can still use that m is equal to e to the fourth. Then, we want to find an interval -r to r so that e to the fourth over 5 factorial times the absolute value of x to the fifth is less than or equal to 0.001 on this interval. Because then, by Taylor's inequality, we have that the error, which is bounded above by e to the fourth over 5 factorial times the absolute value of x to the fifth, is bounded above by 0.001, which is exactly what we wanted. So let's find this interval. We want e to the fourth over 5 factorial times the absolute value of x to the fifth to be less than or equal to 0.001. And now we can solve this inequality for the absolute value of x to find that the absolute value of x must be less than or equal to 0.294. Therefore, the error r sub 4 of x is less than 0.001 on the interval absolute value of x is less than or equal to 0.294, which is the same as the interval negative 0.294 to positive 0.294. And so we're done. Let's get some more practice. First, let's find the third-degree Taylor polynomial of e to the x centered at 2. Just like before, we'll need the first three derivatives of e to the x. Again, this is easy. They're all e to the x. Then we can plug this into the general formula to find that the third-degree Taylor polynomial of e to the x centered at 2 is e squared plus e squared times x minus 2 plus e squared over 2 times x minus 2 squared plus e squared over 6 times x minus 2 cubed. And now, let's use Taylor's inequality to give an upper bound for the error possible in using this approximation of e to the x on the interval 1 to 3. Since we're approximating using the third-degree Taylor polynomial, we first need to bound the absolute value of the fourth derivative of f on the interval 1 to 3. Again, since f of x is equal to e to the x, the fourth derivative of f is, again, e to the x. Just like we found in the previous example, e to the x is increasing, and so it attains its maximum at the right endpoint of our interval. In particular, the absolute value of the fourth derivative of f is bounded above by e cubed on the interval 1 to 3. So, by Taylor's inequality with m is equal to e cubed, we have that the error r sub 3 of x is less than or equal to e cubed over 4 factorial times the absolute value of x minus 2 to the fourth. Again, on the interval 1 to 3, we get at most 1 unit away from 2. Therefore, the absolute value of x minus 2 is bounded by 1 on this interval. So, this quantity is bounded above by e cubed over 4 factorial times 1 to the fourth. And if we compute this number, we get that the error is bounded above by 0.837 on the interval 1 to 3. Let's do one more example. First, let's find the third Taylor polynomial of g of x is equal to cosine of x at the point a is equal to pi over 2. This should be pretty routine by now. In order to calculate the third Taylor polynomial, we first calculate the first three derivatives. Then we can plug in the center, which is pi over 2, and apply the general formula for the third Taylor polynomial to get that the third Taylor polynomial is equal to 0 plus negative 1 over 1 times x minus pi over 2 plus 0 over 2 factorial times x minus pi over 2 squared plus 1 over 3 factorial times x minus pi over 2 cubed. And we can simplify this to get negative x minus pi over 2 plus 1/6 times x minus pi over 2 cubed. Now, let's use the fact that the Taylor series is alternating to determine the max possible error in using this approximation to cosine of x on the interval pi over 4 to 3 pi over 4. Recall the alternating series estimation theorem, which says that the error in approximating an alternating series by the nth partial sum is less than or equal to the absolute value of the n plus first term in the series. Therefore, the error in approximating cosine of x by this third-degree Taylor polynomial is bounded above by the absolute value of the next non-zero term of the Taylor series. If you calculate the next few terms, you'll find that the next non-zero term is the fifth-degree term, which is negative 1 over 5 factorial times x minus pi over 2 to the fifth. Therefore, by the alternating series estimation theorem, the error in approximating cosine of x by its third-degree Taylor polynomial is less than or equal to the absolute value of minus 1 over 120 times x minus pi over 2 to the fifth, which is less than or equal to 1 over 120 times pi over 4 to the fifth, since the radius of our interval is pi over 4. And this number is about equal to 0.00121. Therefore, we have found that the error is bounded above by 0.00121 on the interval pi over 4 to 3 pi over 4.